John. In this episode, we're going to give you an overview of how the machine is controlled and a very basic introduction to the programming language we use to tell the machine what to do when it's cutting apart. As we saw in the first chapter, a typical CNC milling machine has a table and a spindle. The table supports the workpiece we'll be machining, and this table can move side to side and front to back. The spindle is what spins the cutting tool that does the actual machining on the workpiece. The spindle moves up and down relative to the table. The basic milling machine is capable of moving in 3 directions. The motion directions are called axes, and they move like this. The x-axis moves side to side. The y-axis moves front to back. And the z-axis moves up and down. The machine coordinate system defines where the axes can move, and it's how we measure how far they've moved. It basically tells the control where the table and the spindle head are in relation to each other. The machine coordinate system starts at 0 at what we call the machine's home position. On this VF3, the home position for X and Y is here in the front left corner. As the table moves away from this position, you can see that the X-axis position readout is getting more and more negative. We say that we're moving in a negative direction. If we stop here in the middle of travel and start going back the other way, we can see that the position readout is now getting less negative. Now we're moving in a positive direction. The y-axis acts the same way. As we move the y-axis towards the back of the machine, the position readout becomes more negative. So we're moving in a negative direction. When we move forward, the readout becomes less negative. Now we're moving in the positive direction. And, as you might expect, the z-axis also works the same way. Home position is at the top of travel, and as we move down towards the table, the spindle gets more negative. So, for the z-axis, moving downwards is moving in the negative direction, and upwards is positive. So, we looked at the machine coordinate system, basically the values that tell the machine where the table and spindle are relative to each other. Now, let's look at the work coordinate system. The work coordinate system is what tells the machine where the workpiece and the tools are in relation to the machine coordinate system that we just looked at. If we think of our machine for a minute like a GPS map on your phone, then the machine coordinate system might be the actual map of where all the streets and landmarks around us are. And the work coordinate system might be our physical location within that existing map, based on the exact street corner where we're currently standing. In a basic sense, the machine coordinate system defines the size of the world inside our CNC machine, and the work offsets define where the important starting points are inside that world. Now, let's look inside our machine to get a visual understanding of how these offsets work. Our vise is clamped solidly to the table right here, and the workpiece we'll be cutting is held tightly inside of the vise jaws. In this case, our work coordinate, or work offset as it's usually called, tells the machine that this left rear corner is exactly minus 29.65 inches away from home on the x-axis and exactly minus 7.29 inches from home on the y-axis. We've also told the machine that our z-axis work offset is minus 22.73 inches away from z-axis home position. These 3 offset numbers give the machine its starting position for where we will move before it begins machining the part. But that's only half of what our machine needs to know before it can get started. What's the other thing the machine needs to know? Where is our cutting tool compared to home position? Or more specifically, where is the tip of our cutting tool compared to the tip of the spindle. Here's the cutting tool we'll be using right now. The tip of this tool is exactly 5.3 inches from the face of the spindle. This is our tool coordinate, or tool offset as it's most always called. In our example here, with the Z-axis at home position, our Z-axis work offset is minus 22.73 inches from the face of our spindle to the top of our workpiece. And our tool offset for this cutter is 5.3 inches below the face of our spindle. So the control will take 22.73 inch value and subtract the 5.3 inch tool length, and know that the tip of the tool is 17.43 inches above the workpiece at home position. Now the machine knows where everything is located. There are several ways the setup machinist can set these work and tool offsets precisely. We don't need to get into that now. Just understand that until these numbers are entered correctly, the machine doesn't know the location of the part or the length of the cutting tools. As we saw earlier when we were using the machine coordinate system, as we move away from home position, the machine position display increases in the negative direction. But there's another useful position display. Now that we've defined where our part is with work coordinates, we can change to the program coordinates display, which treats our workpiece as our starting point. The control will show us our position relative to the workpiece. As you can see, 0 starts here at the workpiece, and jogging the x-axis, anything this side of the part shows as negative, and in this direction, positive. The same is true for the y-axis, as well as the z-axis. So now we have a general idea of how the machine moves, how it knows where it's at, and how it knows where the workpiece is. Now we need to tell the machine where to move and what to do when it's time to start cutting the part. G-code is a common language people use to tell computerized machine tools how to make things. G-code is basically a list of instructions saved as a program to tell the machine things like what tool to use, how fast to spin the tool, and how fast to move the machine, and where to do the cutting. A G-code program looks like this. It's a long list of specific instructions telling the machine exactly what to do. We'll look at a few of the most common G-codes so you can get an idea of how this language works. Now, although you will always hear machinists refer to this language as G-code, there are actually two basic types of function codes that are used when programming. These are G-codes and M-codes. G-codes tell the machine how to behave or what to do, and M-codes are more like switches that turn a function on or off. Both G and M codes can have letter addresses that provide more information or instruction to the machine. These letter address codes are letters and numbers that come after the G or M code that give the machine all the information it needs about a particular function. For example, the code M03 is the command to turn the machine spindle in the clockwise direction. But it doesn't tell the machine what speed to rotate the spindle. The letter address S is the speed command, so we would program M03 S1000 to rotate the spindle clockwise at 1000 revolutions per minute. Another M code example is M06, which is the command to perform a tool change. So if we enter M06 on its own, we're asking the machine to change tools, but we haven't told it what tool to change. The letter address T indicates which tool to put in the spindle. So we add T2 after the M06 command. Now we have M06 T2 entered, which tells the machine to change tools and put tool number 2 in the spindle. This gives the machine all the information it needs to complete the tool change. So now we know we have G codes and M codes, and that there are letter address codes that tell them exactly how to function. Let's look at how these codes interact with some motion commands from a typical program. We start by telling the machine, change tools to tool number 2. Then we move to the next line. G00 is a command for rapid motion. This tells the machine to move at its fastest possible speed to the position in the address code. So in this case, the Z-axis moves from where it did the tool change down to 2 inches above the part. The G43 and H2 commands have to do with defining the length of the tool, but we'll leave that for now since it's a complex subject for another time. Next we have M03 S2000, which turns on the spindle in the clockwise direction at 2000 RPM. Next is the G01 command. The G01 tells the machine to move in a straight line to a new position at a specific speed. X1, Y1 are the new coordinates we're moving towards, and F20 is the feed rate, or the speed at which we're moving in inches per minute. The G01 command is the basic command we typically use when cutting in a straight line. The F address code allows us to control the speed that we're moving at. In a simple sense, most of the motions that a CNC machine makes are based on 3 G codes. G01, which is motion in a straight line, G02, which defines circular motion in a clockwise direction, and G03, which is circular motion in a counterclockwise direction. The machine is capable of producing extremely complex shapes using just these 3 G codes. We've taken a quick look at how a CNC milling machine moves along its 3 axes. We talked about the machine coordinate system that defines the size of the world inside the machine, and the work coordinate system, which tells the machine where our workpiece and tools are located inside that world. Then we looked at some very basics of how we program a CNC mill to move and cut parts. Currently, there are around 200 G codes and M codes combined in the Haas control, so obviously we're just barely scratching the surface on all of the different ways that you can control the machine using these commands. But as you become more familiar with how CNC programs are written, you'll come to understand the functions these codes perform. And since there are so many codes you can use, we've made it easy to get help remembering what all of them do. Press the Help key while in memory mode and scroll to the G code or M code heading and press the Enter key to see a complete list of G and M codes and the explanation of each. You can also refer to this list in the operator's manual. Thanks for watching, and we'll see you in the next lesson.